There's a mountain in Washington state that millions of people pass by every year without a second thought. It's on license plates, it's in postcards, it's the backdrop of 1,000 hiking photos every week. It looks peaceful, almost frozen in time, a postcard-perfect scene of natural beauty. But beneath that peaceful, snow-covered surface, something is happening. Something that scientists have been watching closely for years, and that recently became impossible to ignore. The mountain is moving. Not in the way most people imagine. Not with fire and ash and dramatic explosions. It's moving in a quieter, stranger way. A way that has kept volcanologists awake at night for decades. More than 2,300 earthquakes shook this mountain in a single event. The largest swarm ever recorded at Mount Rainier. The previous record was a swarm of about 1,000 earthquakes over 3 days in 2009. This new swarm didn't just match that record, it blew past it. And when scientists dug into what caused it, they found something unexpected. By the end of this video, you'll understand exactly what's happening beneath this mountain, why it matters, and what it means for the people who live in its shadow. You'll understand why the United States Geological Survey calls this the most dangerous volcano in America, and why the danger has almost nothing to do with lava. You'll understand the hidden weakness beneath the ice, the towns sitting in the path of a potential catastrophe, and the warning system that could save thousands of lives. Now let's start with what the earthquakes revealed. Under ordinary conditions, Mount Rainier produces around 9 or 10 small earthquakes a month. That's the mountain's normal heartbeat, a gentle, steady rhythm that scientists have been tracking for decades. Every so often it has a swarm, a short burst of extra shaking, maybe once or twice a year. That's considered completely ordinary behavior for an active volcano. But what started on July 8, 2025 was nothing like an ordinary swarm. In the first 12 hours alone, researchers recorded more than 40 earthquakes an hour at the busiest point. The ground beneath the mountain was trembling constantly. The instruments at the Cascades Volcano Observatory were lighting up like a Christmas tree. By the end of the first week, scientists had located more than 1,000 separate earthquakes. By the time the shaking finally slowed, the total count had climbed past 1,350 distinct events. Some researchers believe the real number was even higher once you factor in all the smaller tremors too faint to reliably catch. For comparison, the Yellowstone region had only 1,136 earthquakes in all of 2025, and this single swarm at Mount Rainier surpassed that total. The previous record for this mountain was a swarm of about 1,000 small earthquakes over just 3 days in 2009. This new swarm didn't just match that old record, it shattered it in total number of quakes, in how quickly they happened, and in total shaking energy released. It stretched on for nearly 7 weeks instead of 3 days. It was the most significant seismic activity at the volcano in more than 15 years. And while all of that was happening underground, life on the surface looked completely ordinary. Hikers were still climbing toward the summit. Families were still driving through nearby towns with no idea that instruments beneath their feet were quietly recording thousands of tiny earthquakes in real time. The mountain looked as peaceful as ever. The glaciers gleamed in the summer sun. The wildflowers bloomed in the meadows. No one on the surface felt a thing. The earthquakes were too small to be felt at the surface. The largest was only magnitude 2.4, but the sheer number of them, the persistence, the relentlessness, that was what made scientists sit up and take notice. This wasn't just a volcano clearing its throat. This was something deeper. When scientists looked at all the data, they found something fascinating. The mountain wasn't swelling. There was no sign of magma rising toward the surface. The gas chemistry hadn't changed. The ground wasn't bulging outward. The shape of the mountain hadn't changed at all. There were no unusual sounds, no change in the steam vents, nothing in the webcam footage. Every single piece of evidence that would indicate an impending eruption was completely absent. The answer was something else entirely. Water. Hot, pressurized water moving through cracks deep inside the mountain. Scientists at the Cascades Volcano Observatory quickly determined that the pattern and style of seismicity was not indicative of magma movement. Rather, the earthquakes were being caused by water associated with the volcano's hydrothermal system, not unlike the abundant seismicity that happens in Yellowstone. This is the process scientists call hydrothermal fluid movement. Superheated water pushes upward through tiny cracks in the volcanic rock, and as it travels, it chemically changes the minerals that make up the surrounding stone. The water is heated by the magma chamber deep beneath the mountain. It circulates through the rock, picking up dissolved minerals and gases. And as it moves, it weakens the rock it passes through. Strong, solid rock slowly transforms into something soft, crumbly, and weak. Scientists call this process hydrothermal alteration. It's a process that has been happening inside this mountain for thousands of years, longer than anyone has been alive to watch it. It's the same process that weakened the rock at Mount St. Helens before its 1980 eruption. Core samples from that mountain showed that hydrothermal alteration had turned solid rock into material that was no stronger than clay. It's a little like building a massive snow fort on top of a sandcastle that a hose has been soaking from underneath. Somewhere nobody can see it happening. From the outside, the fort looks completely stable. Underneath, the foundation has been losing its strength one drop at a time. The mountain is slowly eating itself from the inside out, and no one on the surface can see it happening. Chemical analyses of glacial meltwater from the mountain have confirmed that this hydrothermal alteration is still active. Meltwater from Emmons Glacier has been found to contain chloride and sulfate concentrations, consistent with hydrothermal influence. The highest concentrations were found near areas with the most extensive hydrothermal alteration. In other words, the process that weakens the mountain is happening right now, today, this week, while hikers walk on trails above and families picnic in meadows below. So why does this matter so much? Because Mount Rainier is officially recognized as America's most dangerous volcano, and that title has nothing to do with how often it erupts. The United States Geological Survey ranks volcanoes not by how frequently they erupt, but by how many people would be affected if something went wrong. A volcano that erupts constantly in the middle of nowhere can sit near the bottom of the list because there's nobody around to be affected. A volcano that hasn't erupted in well over a century can sit right at the top purely because of what's built up around it. Mount Rainier sits just 54 miles from Seattle and 37 miles from Tacoma. More than 2.5 million people live within view of the mountain. Its river valleys are filled with homes, schools, businesses, and highways. The sheer number of people in the path of potential danger is what makes this mountain so hazardous. Mount Rainier carries the largest collection of glaciers on any single mountain in the continental United States. 25 named glaciers covering 87 square kilometers, with a snow and ice volume of about 3.8 cubic kilometers. That's roughly the same as covering 17,000 football fields with frozen water. It has more than 5 times as much snow and ice as all the other Cascade volcanoes combined. To put that in perspective, Rainier is sitting on roughly 8 times more glacier ice than the volcano in Colombia that killed more than 23,000 people in a single night in 1985. That comparison is what keeps volcanologists up at night. The volcano at Nevado del Ruiz had 0.5 cubic kilometers of ice. Mount Rainier has 3.8 cubic kilometers. In that disaster, the volcano erupted, melted its summit ice, and the meltwater mixed almost instantly with ash and loose rock into a wall of moving mud that swallowed an entire town. Most victims were asleep in their beds with no warning at all. More than 23,000 people lost their lives in a single night. And Rainier has 8 times more ice. And here's the strange contrast at the heart of this story. The volcano that draws the most tourists, the one whose snowy shape appears on license plates and postcards across an entire state, is also the one carrying the single most dangerous lahar potential in the country. Nearly 2 million visitors come to Mount Rainier National Park every year to admire the volcano and its glaciers, alpine meadows, and forested ridges. But as the USGS puts it, the volcano's beauty is deceptive. The single biggest danger tied to this mountain isn't lava. It isn't ash. It's something called a lahar. A lahar is a fast-moving river made of mud, rock, water, ash, shattered trees, and boulders the size of cars, all rushing downhill together at once. The word itself comes from Indonesia, a country that has suffered some of the deadliest mudflow disasters ever recorded. People who have witnessed one describe it as wet concrete moving at highway speed. The USGS describes lahars as the greatest hazard to people near Mount Rainier. Debris flows, which is another term for lahars, can occur with little to no warning and may travel great distances at high speeds. They are among the greatest threats volcanoes pose to people and property. Here's the most important detail in this entire story. A lahar does not require an eruption. It doesn't need lava. It doesn't need any kind of explosion at all. All it needs is heat, water, and rock that has already been weakened over time. A strong enough earthquake could trigger one. An unusually intense rainstorm could trigger one. A sudden burst of glacier melting during an especially hot summer could trigger one. Even an unrelated landslide nearby could shake loose enough weakened rock to send mud crashing into the valleys below. Scientists studying the layers of mud left behind by this mountain have identified at least 11 large lahars over the past 6,000 years. More than 60 Holocene lahars have occurred at Mount Rainier in the past 10,000 years. This isn't a rare anomaly, it's a repeating pattern. When the largest lahars race down the steep upper slopes, they can travel faster than 100 mph. Even after reaching flatter land, they can still be moving at 15 to 20 mph. That might sound almost slow, but this isn't water flowing gently downhill. It's a churning wall of mud and boulders heavy enough to flatten buildings and bury entire neighborhoods in minutes. Roughly 5,600 years ago, a massive collapse of weakened rock carved out a crater more than a mile wide on the mountain's summit. The resulting lahar, now called the Osceola mudflow, traveled well over 200 miles to the shores of Puget Sound, burying entire valleys under debris. It was the largest lahar this mountain has produced in the last 10,000 years. Today, that exact same ground is covered with homes, farms, businesses, and busy highways. People live on top of the debris left behind by past catastrophic mudflows. The Osceola mudflow removed the majority of the hydrothermally altered rock underneath Emmons Glacier, but that doesn't mean the danger is gone. Hydrothermal alteration is still happening beneath other parts of the mountain, and the glaciers are still melting. One lahar in Mount Rainier's history occurred without any evidence of eruptive activity at all. This is the kind of event that emergency planners fear most. A lahar that comes without warning, triggered by nothing more than gravity and weakened rock finally giving way. The electron mudflow, which occurred about 500 years ago, is another example of a major lahar that happened without an eruption. No lava, no ash, just rock that had been weakened by thousands of years of hydrothermal alteration finally collapsing. Now, let's talk about who is standing in the path of all this. Because this isn't some distant problem in an empty wilderness. Roughly 2.5 million people live across the river valleys that could potentially be touched by a lahar from Mount Rainier. Narrow that down to the zones inside a genuinely high-risk lahar path, and experts estimate somewhere between 80,000 and 150,000 people live directly on top of old lahar deposits. Their homes are literally built on debris left behind by past catastrophic mudflows. Lahar flow paths follow the Carbon River and Puyallup River that lead directly to metropolitan areas. Lahars would impact the nearest small towns within a matter of 10 to 15 minutes, and it would reach the larger metropolitan area within 50 to 60 minutes. The town of Orting sits directly in the path of a potential lahar, and is often used as a symbol of the entire risk. It sits inside a mapped lahar hazard zone where local schools run evacuation drills preparing children for a lahar warning going off during class hours. These are ordinary towns with grocery stores, little league fields, and neighborhoods full of families. New houses are still being built inside these mapped hazard zones. Major highways carrying thousands of commuters daily run right through them. Nearly 135 miles of river channels surrounding the volcano were affected by the lahars of May 18, 1980. A mudline left behind on trees shows depths reached by the mud. The same rivers, the same valleys, the same danger. None of it feels dangerous when you're standing there. It feels like home, which is exactly what makes this hazard so hard for residents to hold in their minds day to day. The mountain looks peaceful, the sky is blue, the streets are quiet, but beneath the surface, the mountain is still cooking. The glaciers are still melting. The rock is still weakening. Some towns run evacuation drills in schools, where children practice what to do if a lahar warning sounds during class, the same way other kids practice fire drills. The orange signs with a person running from a wave mark the evacuation routes. Most people don't give them a second thought, but those signs are the difference between a community that gets out in time and one that doesn't. The fact that this could happen with almost no warning time is the reason this region built one of the most advanced volcano hazard monitoring systems anywhere in the world. The Rainier Lahar detection system was established in the 1990s by the Cascades Volcano Observatory and Pierce County Emergency Services. Its purpose is to detect lahars within 5 to 10 minutes after they occur and subsequently alert downstream communities of their impending arrival. The original system used acoustic flow monitors, geophones transmitting at only a few frequencies once every 10 minutes. While helpful, given that lahars are fast-moving, this was not fast enough for timely warning. In 2016, the Cascades Volcano Observatory and Pierce County began upgrading the RLDS. Since then, 25 new stations have been established in valleys and drainages along the northwestern flanks of Mount Rainier in the direction of the Tacoma metropolitan area. These stations operate in the broadband and continuously transmit so that data is always received in real time. 3 new stations were installed along the Puyallup and include tripwires, which will break during the passage of a lahar and send an alert to emergency services. New technology is also being tested for lahar detection. A 2024 study demonstrated the effectiveness of using a laser rangefinder placed on a river channel bank for detecting mass movements flowing past a station. The laser rangefinder successfully captured a small debris flow on Mount Rainier in 2023, confirming its effectiveness as a lahar detection and monitoring tool. This technology could provide an alternative to physical tripwires and improve the speed and reliability of lahar warnings. The warning system connects directly into the state's emergency alert network, and it also includes a physical network of outdoor sirens placed throughout the most vulnerable river valleys. When those sirens sound, it means move to higher ground immediately. Do not wait for further instructions. Do not try to gather belongings. Move to higher ground right now. When a real signal is detected, the sensors closest to the mountain pick it up first, giving emergency workers a small but precious head start before the flow reaches sensors further downstream. Every extra second matters for a family trying to reach higher ground. The evacuation could be as short as 10 to 15 minutes for the nearest small towns. The system also includes webcams updated hourly and seismic stations that help monitor the volcano. The additional stations installed as part of the RLDS upgrade have increased the network sensitivity of the broader monitoring system, making it more sensitive to smaller earthquakes. This helps scientists study the broad West Rainier seismic zone near the volcano, an area that experiences earthquakes unrelated to the volcanic activity of Rainier proper. The earthquakes were one story, but there's another piece of this puzzle that's changing right now, and it has nothing to do with earthquakes at all. Glaciers across Mount Rainier have been slowly shrinking for decades as regional temperatures have climbed. In recent years, the speed of that shrinking has picked up sharply. The glacier meltwater systems at Mount Rainier are extremely sensitive to atmospheric changes. Diurnal temperature changes can cause stream levels to fluctuate by tens of centimeters overnight, in some instances altering the stream channel morphology. Here's the problem. That meltwater has to go somewhere, and increasingly it rushes down the slopes faster than the old drainage channels were ever built to handle. Increased stream discharge appears to dilute hydrothermal influences, but meltwater samples collected during diurnal discharge minima yield low levels of sulfate and chloride in some instances, indicating hydrothermal influence on the subglacial environment. In smaller events, park officials call these debris flows. They're cousins of a true lahar, not nearly as deadly, but powerful enough to tear apart trails, wash out bridges, and force officials to close areas without warning. A small debris flow was successfully captured by a laser rangefinder in 2023, demonstrating that even small events can be dangerous. But the bigger concern is what the melting ice means for the mountain's stability. The glaciers aren't just melting water, they're also weight. Weight that's been holding the weakened rock in place. As that weight disappears, the risk of collapse increases. Hydrothermal alteration has been affecting the rock for thousands of years, weakening it from the inside. The glaciers have been holding it in place, providing weight and stability. As the glaciers melt, that stability is being lost. This is not a sudden disaster waiting to happen. It's a slow-burning crisis that has been unfolding for decades. But the earthquakes of the past year have made it clear that the mountain is more active than many people realized. The glacier meltwater systems are dominated by atmospherically derived waters during the ablation season, with an inversely proportional relationship between electrical conductivity and meltwater discharge. In plain English, more melting means more water flowing through the mountain, which means more potential for triggering the collapse of weakened rock. To understand why this mountain is so dangerous, you need to understand the process happening inside it. Hydrothermal alteration is the process where hot, pressurized water chemically changes the minerals that make up volcanic rock. Strong, solid rock slowly transforms into something soft, crumbly, and weak. The water is heated by the magma chamber deep beneath the mountain. It circulates through the rock, picking up dissolved minerals and gases. And as it moves, it weakens the rock it passes through. Picture leaving a metal spoon sitting in scalding hot tea for hours. The surface slowly changes even though nothing seems to be happening at first. Now stretch that idea across thousands of years deep inside a mountain. The rock doesn't just warm up a little, it fundamentally changes what it's made of. The 1980 eruption of Mount St. Helens taught scientists an important lesson about hydrothermal alteration. Core samples from the mountain showed that hydrothermal alteration had turned solid rock into material that was no stronger than clay. The rocks had been silently failing for years before the eruption. The mountain was weaker than anyone realized. The same process is happening beneath Rainier right now. Large sections of the mountain, especially near the summit, are no longer solid rock at all. They've become weak, waterlogged material sitting on some of the steepest terrain in the region. Geoscientists have published extensively on the connection between hydrothermal alteration and volcanic collapse at Mount Rainier. Studies have demonstrated that collapse-prone, hydrothermally altered zones exist within the volcano. Much of this weakened material is held in place right now by its own frozen weight and plane friction against gravity. Remove that weight, or add more water, and the whole thing could give way. The glaciers have been providing weight and stability. As they melt, they remove that stability. The friction that holds the weakened rock in place is reduced. The mountain becomes more unstable. Scientists have been mapping hydrothermally altered rocks on Mount Rainier using airborne visible infrared imaging spectrometer data. These studies have identified the locations and extent of alteration, helping researchers understand which parts of the mountain are most at risk of collapse. The distribution of altered rock helps explain why some areas are more prone to mass movement than others. So, what does all of this mean? The volcano remains at its normal everyday alert level, the USGS Cascades. Volcano Observatory has confirmed that all monitoring data are consistent with background activity levels in the Cascade Range. There's no sign of magma rising toward the surface, no sign of an eruption on the way. The extra shaking has settled back into the mountain's typical quiet rhythm. But a normal alert level does not mean zero risk. The USGS alert level system is designed to communicate the level of volcanic activity. Normal means that the volcano is at its typical background level of seismicity. But for Mount Rainier, normal does not mean safe. The mountain has been weakening from the inside for thousands of years. The glaciers have been shrinking for decades. The danger is not from magma. It's from ice, water, and weakened rock. For this volcano, normal alert level has never meant zero risk. The primary danger was never really tied to whether an eruption happens. It's tied to the slow, decades-long weakening of rock beneath the summit. Rock that is carrying an enormous and increasingly unstable mass of glacier ice on top of it. Scientists describe this not as a question of if, but of when, on a timescale that could mean centuries from now, or in theory, something sooner. The Osceola mudflow happened 500 to 600 years ago. The electron mudflow happened 500 years ago. These events are not rare anomalies. They're a repeating pattern in how this mountain behaves over long stretches of time. What changed over the past year isn't the basic danger this mountain poses, already documented for decades. What changed is how loudly the mountain reminded everyone it's still an active living system, still shifting fluid and heat through its underground plumbing at a scale nobody had witnessed since monitoring began. The volcano that draws the most tourists, the one whose snowy shape appears on license plates and postcards across an entire state, is also the one carrying the single most dangerous lahar potential in the country. Not because it's the most explosive volcano, not because it produces the most powerful chemical reactions underground, but simply because of geography, because of exactly how much ice sits on top of exactly how much weakened rock, directly above exactly how many people. If this kind of deep dive into what's really happening beneath the surface is something you want to see more of, make sure you're subscribed. If you found this useful, share it with someone who has family or friends anywhere near Puget Sound. Drop a comment and let us know if you've ever visited Mount Rainier or if you live somewhere in the Pacific Northwest. And if this helped you, check out my video on the San Andreas Fault's secret pulse. Stay curious, stay informed. I'll see you in the next one.